Hello everyone, this is Mohsen Saraj. I'm a senior application engineer for Ansys working with Ozen Engineering. Today I want to talk about CFD analysis of the cooling that happens due to the adiabatic expansion. So, adiabatic expansion happens when we have a sudden change in the volume of the gas. Look at this system that we have. We have air flow that coming on through this narrow way, and after that when enter this opening we are seeing that if the system is closed, it means that it is isolated and we don't have any exchange regarding to the heat with the surrounding. Then here we should see that the pressure and the temperature drops. So it means that cooling happen without really any additional energy to the system. So we can use this pressure and temperature drop for as a cooling means for the for industrial applications. And it happens not only in industry, also in geology or in nature. We know that when we have air that, that this air moving going up, okay, warm air when goes up it is cooled down and the temperature drops. So for example in this air we should see more water drops formation as it goes up the hill, and when it comes down then on the other side of the hill we can see then precipitation that due to the raining and snowing that we have. And this method can be used in the data centers and in for HVAC and air conditioning for the building, uh, and also for the cooler and condensation through the adiabatic cooling system that we have. We have many benefits regarding this method. The good things is that it is very energy efficient. As I said, that we don't need any additional work on energy to the system. It could be like a closed system, isolated system, and so the operation condition it is very low. And the good things about this is impact on the water usage and on the other word on environment. This method can save billions of water liters annually for cooling in the cooling system for the data centers or other industrial applications. A little bit about the difference between adiabatic cooling and Joule-Thomson effect. Basically, although they are similar thermodynamic process for that cause reduces the gas temperature, but they are doing this in different way. In adiabatic cooling, as I said, that it is mostly rely on the expansion of the gas in the closed system without really any heat exchange with the environment. But Joule-Thomson mostly rely on the sudden change in the temperature in the pressure. So that it is not necessarily is with the significant volume change. So although they are similar, but they are basically different in the way that they drop the pressure. So let's move on to the Fluent and see that how we can model this effect in Fluent using Ansys Fluent tool. Okay, this is a space column and this is the model. As you can see that we have a smaller part and bigger or larger size part. For the smaller part, the radius it is 50 millimeter, and for the larger size it is 200 millimeters. So the ratio it is 1 to 4 between the uh, between the radiuses, the radius, and each part it is long enough that we can have a fellow fully developed. Also, I assign names to the model. Okay, as you can see, inlet, outlet, and also lateral part it is for the walls. So pretty much simple problem that we have it here, and we use it then for in Fluent meshing and then for running the model in Fluent itself. This is the model in Ansys meshing, Fluent meshing. I imported the geometry. We don't need a local size, and then for surface mesh, this is for 2 millimeter minimum and 30 centimeters maximum. Let's see the surface mesh. Okay, you can see that not bad. Specifically here, we can change it if we need it later. Only fluid and uh, internal interfaces going to the fluid boundary, no share topology, and no uh, multi-zone meshing. Inlet outlet walls for the boundaries that we have. Region, it is only fluid, and I consider 5 layers for the for modeling boundary layer. And let's work on the volume mesh. I just consider minimum 0.15 for the orthogonality. Volume meshing, you can see that not bad mesh that we have. Boundary layer, and this is the polyhedral mesh that we have. So this is the mesh that we have. So check the orthogonality. Minimum it is 0.41, which is very good, and about 60,000 cells. Let's use this mesh and send it out to to Ansys Fluent and set up the model for Adiabatic expansion. Okay, in Fluent we read the mesh. As you can see that it is a steady state pressure pressure based solver. Let's see the mesh. Inlet, outlet, and this is the opening that we have that you can see. So this is the mesh that we have, and if we check the quality, the orthogonality, it is above 0.4, which is very good, the minimum orthogonality, and the mesh info is or this for each partitions. Total it is about 60,000 polyhedral cells. For material modeling, I just consider constant uh, properties everywhere for the air. Keep it as is. And for boundary conditions, inlet, I consider mass flow inlet. We need to enter the value for the mass flow rate. Here I consider 30 kilogram per second, enter the domain. Keep the rest as is. And for thermal condition, I consider 80 degrees Celsius. I change the unit from Kelvin to Celsius. And please note that this is total temperature. So it is a summation of static temperature and isentropic temperature together. This is for the inlet condition. For outlet condition, pressure outlet, this is the gauge pressure, ambient pressure that I consider here, and same thermal condition for the outlet as inlet. And operating condition, I consider 0 here. And this is the way that is we can use the same operating condition as set up for the pressure outlet when we change the material property, material model from constant material properties to ideal gas. So these are the setup for material properties. Methods, almost is by default. Be sure that I just consider the second order upwind condition. For report definition and monitors, I already define three monitors there to report max temperature, mean temperature, and max velocity in the domain. As you can see, for the domain it is volume report. For the max temperature, this is for the mean temperature, and this is for max velocity. So these are the setup that we have. Let's initialize the model. As you can see, I consider gauge pressure, zero velocity everywhere, 38 degree. It is almost around 80 degree for total temperature. Initialize that, and if you can here also, before going for running the simulation, I also define a plane symmetry. It is YZ plane. As you can see here, I can put it in this way. Okay, it is YZ plane that we have it. It is easier to see that in this way. And either I define some contours on this symmetry plane. This is for the temperature, everywhere 38 degree. Pressure everywhere 101 kilopascal, and velocity is zero everywhere. So let's start running the simulation. I just consider 500 iteration, and then I'll check the residuals and uh, mass flux imbalance to see that if it's good or not, and also according to these monitors we can check that. So this is the residuals. You can see that the temperature increasing, minimum temperature, this is the mean temperature. Max temperature is almost at 80 degree, and quite high velocity for in the domain above 350, so 370, something like this. So you're getting almost constant max temperature, but the mean temperature is still changing. Is started to getting flattened, but we have to see. So almost 50% done. I will back to you when the solution done for 100%. Now we are getting to the end, 95%. You see that mean temperature now is about 80. Mean temperature, this is mean temperature, it gets to the 80. Okay. Max temperature same at 80, and max velocity is about 370 meter per second. Let's check. This is the contours of the velocity. As you can see, let's check for the temperature. You can see that, okay, that we're getting this temperature weird results that we have. So it is back to the basically to the material modeling. Let's change it from constant properties to ideal gas and see what's happened. So again, we have ideal gas for the material. Let's again initialize the model, the problem, and restart again the solution. You can check the contour of temperature to see that everywhere 38 degree initial temperature. Let's see. So we started the solution. These are residuals. This is mean temperature. It is fluctuated at the beginning. Max temperature, it is a hike at the beginning above 90 and then it back to 80. And still the velocity, you can see that 370 something. So let's check the minimum temperature because we are looking for the cooling. Almost 11 or 12 degrees Celsius. I'll back to you when the solution done. Okay, above 95%, almost done the 100% the solution. Not very low residuals, but let's check for the mass flux and also heat transfer rate. For mass flux, choose everything and compute. Pretty small net results. And if we check the total heat transfer rate, again is this value. And you can see that this is only both for the mass flux and also heat transfer. It is from the inlet outlet, because everywhere else from the walls it is like isolated insulated wall. So if we check the mean temperature, you can see that 11.8, which is very good. Max temperature 80, I guess, yeah, it should be 80 somewhere here. And velocity, it is 371, close to the constant property that we have. But the good thing is that we, for when we consider ideal gas, we could capture minimum temperature much lower than 38 that at the beginning that we have. Let's look at the graphs and contours for the temperature. Okay, let's see. You can see that warm air coming, and after entering this sudden expansion we see much lower temperature here, that is about 12 degree. So, and this cooler zone expand through this and penetrate in this area. So it means that when I have sudden expansion and when I don't have any heat transfer through the walls, which is adiabatic system, this causes this expansion to the gas volume causes the temperature drops. As we can see that from 38 it drops to about 12, and if we look at the temperature, it is about 12.5 that we have it here. Let's look at pressure. So this is, you can see that the minimum pressure is about 83.9, about 84 kilopascal. As you can see that as the gas flows inside the expansion, the opening, we see this area that the pressure also drops. So this adiabatic expansion causes not only the temperature drops, also the pressure drops. So as you can see that it is about 370 meter per second high velocity that we can have. So in this simple example that we have this opening, we could show you that we can have cooling happen due to sudden expansion in the closed system, that we don't have heat exchanging with the environment, and this expansion to the volume causes temperature drops, and also velocity accelerated, and also pressure drop in the system that we have. We work on a similar geometry of the opening, but instead of the ratio of the radius diameter is 4 to 1, this model it is 10 to 1. Let's open space claim. This is the model in a space claim, same radius of 50 for the thinner part, but the opening now it is expands to 500 millimeters. It used to be 200, so the ratio of the pipes it is 1 to 10. This is for the geometry, and let's check the mesh. This is the mesh. We use same setup for the meshing, and if you look at the uh, volume mesh, you can see that. Okay, this is the smaller pipe, this is larger pipe, boundary layers, and we use the polyhedral meshes. As if we check the quality of the volume mesh, the orthogonality, it is minimum orthogonality, it is 0.32, and the number of cells, as you can see that minimum volume is positive, and number of cells is now about 200,000, that here we can see. So this is the mesh that we have it. The no local size, and after that I follow the same setup for the another geometry that we have. Let's go to Fluent. This is the mesh that we have, as you can see, inlet, outlet, and the walls. If we check the mesh quality, as you can see, the 0.033, the minimum orthogonality, which is good. And if we check for the info, you can see that is about 199,000 to 100,000 cells that we have. Let's check the inlets, the boundary conditions. 30 kilogram per second as before. Okay, 80 for the 80 degree for total temperature. For the outlet, pressure outlet, again I use gauge pressure 101 kilopascal, and backflow total temperature of 80 as before. Apply, because you remember that I have to use ideal gas for the air, for the gas that we have, ideal gas model. So that's why in the operating condition I have to use with zero operating pressure at the reference point, and then set the gauge pressure for the outlet or inlet pressure with ambient pressure. So be sure about this setup for the operating pressure when using ideal gas. And back to the boundary conditions, walls, as you can see, thermal, it is adiabatic, no heat transfer from the walls. And when I go to initialization, let's consider 38 as before, initialize the model, check the contours. As you can see here, initial temperature 38, zero velocity everywhere, and pressure it should be 101. Yeah, as you can see here. So let's start running the calculation, and you remember that I already have these report or for the monitoring the max temperature, mean temperature, and max velocity with the same definition that I had it before. And let's start calculation. These are the residuals. This is for the max temperature. This is mean temperature, and this is max velocity. I'll back to you after the solution is done. We almost done for the solution, 95-96%. As you can see that the mean temperature, max temperature, and max velocity are almost constant. So the solution completed. The residuals at order of -3, -5, -4. Max temperature, it is almost 80, the initial temperature. Mean temperature is around 15 degree Celsius, and max velocity is about 360 meter per second. Let's look at the pressure. So if the pressure, we consider the contours for the pressure, again you see that the drops in the pressure from 100 and 101 at the initial, 101 kilopascal the initial, to 88 somethings. Look, check the graphs. Yeah, 88, as you can see. So we have pressure drops. For the temperature, this is the contours of temperature, as you can see, because the same amount of mass flow rate enters the larger area. So you can see that the temperature decreased to 16.8 here compared to 11.8 that we have it for the ratio of 4:1 for the diameter. So larger expansion gives less effect on the same amount of the air for the cooling. So this is just showing that the metric, if we want to know that the effect of the distance between openings when the hot air or warm air coming into the open area, that we use it for cooling. So the cooling zone is affected by the distance between the or the ratio between the diameter of the smaller and larger pipes, and also maybe the distance between the openings that we have if we consider cooling using this technique for cooling of the open areas like data centers or whatever. So this is something to take a note of that. yeah, in the symmetry plane, 357 meter per second. Be sure that to always check the mass imbalance and heat transfer balance. If we check everything, you can see that inlet outlet that we have. This is important. Inlet outlet that we have, the results is the net results is 0.0017, still small, and no heat transfer from the walls, you can see 0, and the difference between inlet incoming uh, heat from inlet and outgoing, it is about 1043. So this is the way that we can check the imbalance into the system. We can run this model further more to see that what's going on, but the intention in this example to show that when we have sudden expansion to the gas volume, we can use this technique as a mean for in industry for cooling, that for temperature drop, and this happen without any input energy to the system, which is good and make it one of the good candidate for industrial cooling. So I hope that by this example I could just show the proof of concept of the adiabatic cooling due to the adiabatic expansion. Thank you very much for following up with this example.